Welcome! For second-order RLC circuits, resistor, capacitor, and inductor circuits, this video explores response damping cases in both series and parallel RLC lumped element circuits. Damping cases for RLC circuits come from the solutions for voltages or currents. Shown here is the solution general form for series RLC current. More specifically, damping cases come from characteristic roots within the solution process. This equation for S1 and S2 is the characteristic roots equation for series RLC. These three series RLC damping cases come from the previous characteristic roots equation.
If you would like more background on RLC circuits before exploring second-order damping cases, please check out this video on the first and second-order circuits and equations YouTube channel.
This discussion of damping cases applies to series RLC, parallel RLC, time domain step, and natural responses. The different damping cases for RLC circuits are determined by the values for R, L, and C. To start, we'll explore damping qualitatively in terms of resistance R. Current through resistors means loss, dissipation of energy. Resistor current in RLC circuits means more damping. For parallel RLC, greater resistance means less damping. This is because currents in the inductor and capacitor do not need to go through the resistor. When the parallel RLC resistance increases to infinity, that becomes an open circuit. The parallel RLC becomes an ideal LC tank circuit with no loss at all. Conversely, lower resistance for the same parallel RLC voltage that drops across all three components means more resistor current and therefore more damping. Current is taken away from the capacitor and inductor. The resistor current is lost to dissipation. Series RLC circuits have only one current, which must always go through the resistor. For series RLC, less resistance means less damping. For series RLC, when resistance decreases to zero, the resistor becomes a short circuit. With no resistance, the series RLC becomes an ideal series LC circuit. Here we have the characteristic roots equations for both parallel and series RLC. Notice how the parallel RLC characteristic roots have resistance R in the denominator. More resistance means less damping. The series RLC characteristic roots have resistance in the numerators. More resistance means more damping.
Detailed analyses on the content in this video are available in Chapter 14 in this book. The equation numbers 14.42a and 14.42b are on pages 259 and 261.
The relative sizes of the terms under the square root signs determine the three damping cases: overdamped, critically damped, or underdamped. Let's look at how these criteria for the three different damping cases affect the solution equations and responses. The criteria for overdamped response is that the quantity under the radical sign is greater than zero. When those overdamped characteristic roots are inserted into the solution equations, the resulting equations have two terms of exponential decay. The resulting overdamped response curves look like this one. The criteria for critically damped response is that the quantity under the radical sign is equal to 0. The terms under the square root sign disappear completely from the roots equations. We need a t-term for a second unique solution for critically damped response. Resistance in the numerator for series and resistance in the denominator for parallel. The resulting critically damped response curves look like this one. The criteria for underdamped response is that the quantity under the radical sign is less than 0. This makes the quantity under the square root negative, which can be expressed as an imaginary term, as shown in equations 14.64a and 14.64b. The resulting solution equations are complex exponential terms, which include a damping term, sigma, and an oscillatory term, j omega d. These equations can be converted into trigonometric terms. The result for underdamped RLC looks like the decaying oscillatory curve shown here. Summarizing series and parallel RLC response together, look at the discriminant, the quantity under the square root signs. For overdamped, the discriminants are greater than 0. For critically damped, the discriminants equal 0. For underdamped, the discriminants are less than 0.
Thank you for watching and learning with us.